Hi everyone, welcome to this new seminar. And for today's seminar, we will hear from Claudio Lasarte from the University of Valencia. So Claudio is visiting us for a few weeks, so feel also free to chat with him after the seminar. But for now, it will be about gravitational synchronization in boson dark matter at mixed neutron stars. You can ask questions during the talk or at the end, as usual. And thanks a lot, Claudio, for being here, and you have the floor.
Thank you very much, Theodore. Well, my first talk in Europe was here in America. I remember I was really nervous, like today. No. But probably less than that day. But for me, it was very special. And now coming back to Aveiro again is also special. And that time I talk about broken stars. I promised myself to not talk again broken stars. But at the end, I will do it at the end. Just at the end. Just few slides. And the talk today is related to a project that first came as a side project, but it's starting to have or to turn to be one of my main projects as well. The results are very interesting for us, and I hope that also you can find interest. So do not please pay attention in the typo to synchronization. Will be many, but you know what kind of synchronization we are referring, right? Okay, this project is titled Gravitational Synchronization in boson dark matter at mixed neutron stars. Sorry for that long name. And you can find the details in this paper that we present to arXiv and also submit to a physical review letter. Now it's under revision of the referees, well, the second revision, and we'll see the next month what happened with this work. So I did it in collaboration with Nicolás Sánchez Gual, when José Antonio Font, and well, let's start. A quick introduction. Well, until now, no dark matter candidate have been found. And we think that observation of the string astrophysical system can provide complementary proof for this search of dark matter. In particular, neutron stars, with its strong gravity and supernuclear densities, stand as natural laboratories for this kind of purpose. Happily, we are getting an increasing number of multi-messenger observations of neutron stars. And those observations have started to offer us constraints to our neutron star models. Interestingly, the gravitational waves that we are measuring, coming from binary compact objects, merges, are starting to give us some objects that we can identify clearly if it's a neutron star or a black hole. In particular, not a neutron star because the masses of these objects or can be one of the very massive neutron stars or even goes beyond the mass limit that our models of neutron stars predict. Besides that, also the observation from pulsars have given us some constraints that you can see here, but we don't know exactly the equation of the state or the description of the nuclear content in the neutron star. So we have different equations of the state, some of them match perfectly or match more or less good with the constraint that we have. But with this new constraint coming from the gravitational waves, we are starting to have some tensions in our models. Okay? These ideas motivate the inclusion of an additional component of matter in the neutron stars. In this case, dark matter, to solve these tensions, as for example, Fabrizio Di Giovanni and Sánchez Gual present in 2021 when they include dark matter to this new model, to these models, and try to match in a better way the constraints. In particular, we are focused on bosonic dark matter. You will see in the following videos. Okay, when we model the neutron star matter as a perfect fluid, as a fermionic perfect fluid, and the bosonic dark matter as a complete scalar field, what we have is the Fermi boson star model or configuration. Sometimes I will call it as mixed star, and sometimes as a fermion-Boson star, but it's the same. Ground states are non-linear stable, and that was shown by Valdez Alvarado and collaborators in 2013. But they all, and as you can see here in this 2D plot, we have the parameters of the scalar field and the parameters of the central value of the rest mass density of the neutron star. And the points inside this green line are the stable configurations of these fermion-Boson stars. But more interestingly, they found that also the radial modes of the fermion sector are changed due to the presence of the bosonic matter. For example, in the black line is the configuration of with zero bosonic content, which means is the pure neutron star, and you can see this peak for the fundamental mode, and this peak for the first overtone. But if you include progressively dark matter at 2.5%, 5, and so on, you start to have these peaks. These are additional peaks. This is the power spectrum density of the power spectrum Fourier transform, actually, of the rest mass density in the fermionic star. So they already found that including that matter, we can modify the spectrum of the neutron star. Okay? Some years later, in 2020, again, Di Fabrizio with Nico and people from Valencia proposed a dynamical formation mechanism. In this case, what they did was let the scalar field around the neutron star accrete and let it cool gravitationally, finding fermion-Boson stars. Interestingly, they found some configurations with one radial node or two radial nodes, which means excited bosonic configurations that were long-lived, something that was unexpected because in the case of pure Boson star, those excited states are stable and decay to the ground state. So what they did after this paper was study the nonlinear stability of those excited states, and they found that they in fact are stable. They reproduce the same two-parameter plot or domain of existence of the ground state fermion-Boson star, but now here for the excited stars, the first excited Boson star, fermion-Boson star, sorry, and they found here the region of stability of these new excited states. And they understood that in this case, the stabilization mechanism is given by the fermionic part of the star. Okay. Our idea to continue this work was trying to explain how that fermionic part stabilized the bosonic states. Okay, let's go to the framework. It's really easy, actually. It's basically, I know most of you, or all of you know this Lagrangian. It's a Lagrangian for the scalar field, in this case, the complex scalar field with a massive potential, given by this mu, which is the particle mass. And in this case, we are including the Lagrangian density for the fluid. Those matter contents are only coupled gravitationally. And we can deduce if they are only coupling gravitationally and minimally coupling gravitationally, we will have a stress energy tensor given by the two components of the matter, the fluid and the bosonic part. The bosonic part is given by this stress energy tensor, and the fluid by the perfect fluid prescription. Here in particular, we can find the primitive variables of our fluid given by the rest mass density, the specific internal energy, the pressure, and the four velocities. And in this case, we solve numerically the equations that describe the evolution of this system, basically the Einstein equation, the Klein-Boltzmann equation, fluid conservation equation for the fluid, given by the energy momentum and varying number conservation. But we have to close this system of equations using an equation of the state that is giving us the thermodynamical behavior of the system, well, of the fluid, basically. In this case, we choose the equation of the state given by the ideal gas. It's given by this relation. We have the specific value of this adiabatic parameter given equal to 2. We restrict our simulations just to the spherical symmetric case, and these were done by our code of our group, NADA. which is very interesting because it has a new method like the PIRC methods. Well, it's using the BSSM formalism for the evolution of the space-time, the Walesian formulation for the evolution of the hydrodynamics variables, but also has a logarithmic grid patch that is useful for allowing the external radius to go to very, very big values. That is very useful for our simulations. Okay, after presenting the physical results, I think it's important also to stress that we are doing approximation through numerical simulations. They have to fulfill some criteria that tell us that we are having physical results. And that is through the local and global convergence of the constraints. In this case, our Hamiltonian constraint, as you can see here, present a local convergence at second order, which is something that we expect our method, the PIRC method, is a second order method. At different times, you can see this, the radial profiles or the absolute value of the Hamiltonian constraint, as you see. And well, at equal to 0, it's perfectly second order. Then it's not that perfect second order, but it's very acceptable given these long time evolutions. And in the same case, but for the global convergence, in this case, we have the delta norm of the Hamiltonian constraint. Here, we can see the different values of this in time for different resolutions in our approximations. And in the inset plots, you can see how they scale at second order after escalations. So, okay, we trust in the results. It took some time to have the correct convergence. So I'm very happy for these results. And let's go to the physical ideas that we can draw from the results. The first idea is about the multi-state bosonic configurations and the dynamical synchronization that we observe in these results. Okay, our first scenario is the formation scenario that Fabrizio did. In this case, we have a TOP star plus a Gaussian scalar field given by this initial data, as you can see here. And in these two columns, we can see different panels where we are plotting the radial dependence of the module of the scalar field with different times, with different snapshots here. And each row corresponds to the same time windows. For example, you can see these times here, these times are inside this time window here. This panel corresponds to the fast Fourier transform of the real part of the central value of the scalar field. So it's connected to these radial profiles. And from the left to the right, we identify the different peaks with the states of the bosonic field. This is the ground state, this is the first excited state, the second excited state. In this case, for example, we see that we have two more or less equal amplitude peaks for the first and the second excited state. And that means that we will see in the radial profiles two nodes and also one node. If we go the evolution, we let the evolution, we will see how a gradual transition happens where the nodeless configuration starts to grow. And as you can see, the second node starts to disappear. There is only one node, but not that clear. But then, when we let the ball more time, the ground state is the dominant peak. Here, you can see no nodes in most of the time snapshots. But if we check properly, we also have a third excited state persistent in the evolution. And that can be seen in this node here. So if we let the evolution more time even, to this time here now, we will see that both states are present and more or less with the same amplitude. So what we are having here, what we thought at the first idea was, okay, maybe we have is a multi-state instead of just one single state configuration. How we can characterize this? How can we prove it? In fact, we have a multi-state. Well, we propose some equations. But first, what we did was take the logarithmic scale of the previous plot. When we take the logarithmic scale, we found out that there is not just two peaks, the ground and the first excited state. We have more peaks. as you can see here. And well, I repeat this evolution for different parameters of the scalar field and also the central rest mass density, and I found that this behavior is present in every of our results. And more interestingly, these peaks are like separate in the same distance around the central value, around the ground state. So we started to see some patterns. The first thing that we did was, okay, in this case we have the real and the imaginary part of the scalar field at the central value. They have the same frequency peaks and also the same amplitude peaks. We test this for different points in the star, and we understood that the ansatz for this case should be this. We have a summation of the states given by these complex phases with a specific frequency and also its radial amplitude, depending obviously of the radial coordinate. Okay, so we understood that these plots are telling us, or is telling us, that we need to modulate the system like this. Okay, we go further, and we understood that if we have these ansatz, this will lead to non-stationary energy density systems, given by just computing the modulus square, because we know that the modulus square participate in the stress energy tensor, and in consequence in the density and the energy density of the system. We have these terms that don't depend on time, but these terms depend on time. So we will have here, given we are studying spherical asymmetric configurations, this will represent radial oscillations in our bosonic content. Okay, so this system is not stationary anymore. Okay, in the Einstein equations, we can also propose some solutions for the fermionic matter content and also for the behavior of the space-time. We propose it in this way, where these cosines have the same frequency given by capital omega. And we said, okay, we know that synchronization is a universal behavior for every coupled system. In this case, these two components of matter are only gravitationally coupled. We will expect that they synchronize. If they synchronize, they have to fulfill that these frequencies at the level of the Einstein equation, these frequencies have to be the same of this frequency. So since the parity of the cosine, we found out this relation just comparing these two frequencies. Okay, because when we do the comparison, we have to add a plus minus here. So then there appears a plus minus here, and we just put this to the right side of the equation. So basically, the synchronization relation that we found is that if we have two bosonic states, they have to, they are connected to one fermionic radial oscillation or an oscillation also in the space-time given by this relation. So we verify that. We took, for example, the ground state, the frequency of the ground state. We add and subtract the value of the fundamental frequency of the neutron star here. And we found that the value is exactly the omega minus 1 and omega 1. And we did the same for the other values, the first harmonic and the second harmonic of the neutron star oscillation, producing the omega 2, the omega minus 2, the omega 3, and omega minus 3. Okay, we are producing a multi-frequency, not just a multi-state, a multi-frequency bosonic configuration, which is connected to the different oscillations in the neutron star part. But in particular, this state, which is the state for the first excited scalar configuration, is connected to this second overtone through this equation. And you can see that this is the dominant peak here with this. These two are the dominants. But also, if you see in the neutron star spectrum, which is the purple line, this peak is also dominant in comparison to the fundamental mode. So that means that we are not only having a multi-state and excited states surviving, we also have new dominant neutron star modes that are connected to the bosonic states. Okay, we receive a good perception of one of the referees in the letter, in the journal. And that perception, was about, but well, was a good perception, but also has a question. And the question is, you use a specific prescription for the equation of the state. What happens if you change it? Your synchronization mechanism change or not? So what we were doing this month was test our mechanism of synchronization for different equations of the state. We took two sets of equations of the state. One for the ideal gas with different compactness. But basically, here it should be different stiffness, different values of the compactness related with the parameters of the equation of the state. And also another group of equation of the state, a realistic equation of the state given by this case the DD2 and LSY, but in the version of piecewise polytrope, which is easier for computational resources and also for the simulations. So we construct the TOB stars with this new equation of the states, as you can see here. This is the mass versus radius relation, and we repeat the simulation for the formation of the mixed star. What we found is, for example, here in these two panels, you can see the time windows here, appear several peaks. Well, you can see here the green one, for example, they are superposed, they are not really clear, but well, they are there. And the gray one is our fiducial case, the gamma equal 2. The green one is here with this gamma 1.9, the pink one with 2.1. And after some evolution, you can see that, for example, the pink one still have the excited state percentage there dominating the evolution. The green one, no, the green one has the knowledge configuration dominating the evolution. And our fiducial is like the middle case. But still, you can see the multi-state configuration present for long times. And the same for the case of the realistic equation of states. In this case, these evolutions were called evolutions. We don't have the evolution in the thermal part. And that could explain more or less why at the beginning the peaks are slower than these peaks. But then, if we let evolve enough time, we will also see the multi-state configuration here with two peaks for the case of the LSY, and these two peaks for the case of the DD2. So the first result from this analysis was that the multi-state configurations are independent from the EOS prescription. Okay, now let's validate if our synchronization relation also satisfies in this case. In this case, what we did was just analyze the dominant modes here, which are the overtones, and the overtones here connected with the ground state of the bosonic part given by these relations. And well, it's a bit difficult to see all the detail because there are many plots superposed in each channel. But we verified quantitatively that in fact we have the synchronization relation fulfilled in each case. So that means that the universality of our gravitational synchronization that we found. Okay, let's try to characterize a bit more this scenario. We studied so far just the formation through the accretion of the scalar field on the uniform graph. But what happened with this synchronization mechanism in the case if we have a more controlled scenario? Let's start as an initial configuration, a fermion-boson star with only a single frequency state. Will appear also the synchronization in this case? Okay, what we did was take the excited bosonic fermion-boson star, the first excited, which means the one that has one node in the radial profile. And you can see here, for example, this is the Falk-Fourier transform of the central mass density of the central red mass density of the fluid. And you can see how in the different time windows, there are some peaks that hold the value, no, the amplitude. But in particular, there is one peak that is starting to grow and dominate. No? This peak is the second overtone. The second overtone that I mentioned before that was dominating. And what we check the bosonic content in this case, and what was happening is, okay, the system start with a frequency in the excited state, but then start to appear the ground state frequency also. And when it start to appear the ground frequency also, this peak of the second overtone start to increase. So in this more controlled scenario, we're having a resonance effect as a feedback procedure. As this excited state is stable, and the ground state, of course, is also stable, both are participating, the ground state has started to grow, and that coexistence between those states allows also the growth of this, this mode in the neutron star. So now, when we see new dominant modes in the neutron star spectrum, we interpret it as resonant effects due to the synchronization between the both components.
Can I just ask you, so here you didn't decrete any further scaling field, you just let this evolve?
Exactly. It's an initial configuration in equilibrium without any extra field. Just the scalar field of the Fermi bosons. Okay. This slide, I think, this one and one more to finish about this topic. We ask ourselves if we can characterize more even this mechanism, but in terms of the dark matter content. In this case, we are studying a bosonic scalar field with a massive potential. Let's try to characterize it with the bosonic particle mass. But we need repeat again our formation scenario, but with different values of the scalar particle mass, as you can see here. With these different values of the mu. Surprisingly, what we obtained was, not surprising, but we didn't expect it at the beginning. Okay, we have again the multi-state configurations, 2 peaks, 2 peaks, 2 peaks, 2 peaks. Okay, but if you check it properly, for the case of mu equal to 0.25, there is a limit here, exactly in that value, and the same for the 0.5. And the same for 1, and the same for 2. What this means? We're obtaining frequencies of states that are bound states, given by this relation. We already know which is a bound state and have to fulfill this relation to be a bound state. Okay. This means that if we subtract these two frequencies and form the new dominant neutron star frequency, it will also satisfy that is smaller than mu. Okay. But not also smaller, as I said, is dominant. For example, you can see here in the Fourier transform of the fluid. For the case of mu equal to 0, this is the case for a pure neutron star. We didn't put a bosonic content here. You can see here the peak, the dominant peak. If we include the bosonic matter with the different masses of the bosonic particle, you can see also that there is a superposition here of this peak for different values. But now we have new dominant modes, for example, in the orange one, in the green one, in the blue one, in the purple one. So we have these dominant modes from the bound state, which is something now that is expected, and that helped us to realize that we can map these bound state frequencies onto the domain of existence of the Fermi boson star. You can see here in these lines the domain of existence for the ground state and the first excited state of the Fermi boson stars. And we identify these frequencies for the case mu equal to 1 for different cases, and we found out that they have the same binding energy, which is something that we also didn't expect. Okay, so but this property helps us to, if we want to construct this frequency, for example, in principle, we knew that we need 2 frequencies, right? But since we can construct this domain of existence, and we know that the synchronization will happen when the 2 states, the ground and the first excited, have the same binding energy, we can avoid this, computing this, only knowing this, and recompute the values of these new dominant modes. But in this case, versus the ground state of the frequency ground state for different values of central mass density. This is a way to predict these new dominant modes in terms of just one parameter of the bosonic, not in terms of two, because we know that these two have to fulfill the same binding energy. Until now, these are all the results that we have, but we also saw the potential of these results, and we present some perspective and some future works here. But first, let's draw some conclusions. We have proposed a new path, or we are proposing a new path to detect ultralight bosonic dark matter. This path is through the gravitational synchronization between the two components of the star that we show that emerge naturally from our simulations. And this mechanism leads to a spectrum of bosonic frequencies that resonate with the neutron star radial oscillation, producing long-lived, multi-state, multi-frequency bosonic modes that are also connected to the new dominant modes of the neutron star. Okay, thanks to the independence of these mechanisms from the equation of the state, this opens the possibility of existing universal relations, which are relations between the frequencies of the oscillation of the star with the macroscopic parameters, independent of the equation of the state and the internal structure of the star. For this case, we think that we need to go beyond to the radial oscillations and go to evolutions in 3D without imposing spherical symmetry. So we started some simulation of mixed stars in the Einstein tool, as you can see here. And this to give, I'm showing the rest mass density of the neutron star and the real part of the scalar field. These are good news. Interesting, what we found is that in this case, as you can see, this spherical shell here in white is the presence of the nodes. The node is still there, even this evolution. The bad news is that evolution have a spurious break of linear momentum. So what we need to do here is check properly what is happening, but we think that changing the solver in the Einstein toolkit for the fluid content would help us to avoid these spurious effects. But happily, even with those spurious effects, the node is still present. And if the node is still present, that means that in 3D also we maybe can find multi-state configurations. Well, how can we relate this result to gravitational wave asteroseismology? Well, maybe we can start doing or studying this synchronization in rotating fermion boson stars, which is a project that we also have in mind. We also are working on it. But if we focus only in quasi-radial oscillations given by m equal to 0, this can also couple to m equal to 2 modes in rotating hypermassive neutron stars. For example, in this plot, you can see the Fourier transform of the pressure of this star given by this work by Jorlas and collaborators in 2011. And you see how this mode, which is the mode that is dominating in the production of gravitational waves, produce these two small modes from the coupling with the m equals 0 modes. If our mechanism enhance the radial oscillations, we will increase the value of this peak and also the value of these two peaks. So maybe these two peaks can also participate in the production of gravitational waves, even if it's only quasi-radial modes. And finally, we ask ourselves what will happen with the magnetic field of the neutron star if we have this mechanism of synchronization. And it's also probably that we already started with collaborators. So for the bosonic fermion bosonic star, this is all the results I want to present today. But as I told you at the beginning, I will also talk just a bit about boson star, rocket star, sorry. Since we want to propose to Carlos, Eugene, and the group here a project about rocket stars. Also, if you like this project, we also work on this project, of course. Another previous, like a quick summary of my last results in this year in the PhD. You know basically that I'm coming from, well, I'm Peruvian, but I'm coming from Mexico, it's the master lab. So I work Mercuriere, we got some L-Procastar configurations, then we evolved it in Valencia with Nico, with Tom. These, well, sadly, we found that they are unstable, but was something expected because the spherical Procastar for a single field are also unstable. So we like enlarged the landscape of these configurations. But the interesting result is that even if you have multi-field configurations that couple gravitationally and form spherical symmetric configurations in the density, in the energy density, the evolution shows that all these fields with different multipolar structures migrate to a dipolar configuration. You can see. And form energy density given by a spheroidal configuration. Okay. We ask ourselves if we can find in equilibrium these configurations given by different fields, all of them with dipolar configuration. So we want to propose that to Carlos Origin to try to find those systems. But we also started to think, since there is an interest about the polarization of Procastar, because if you have scalar Bose-Nassar, you don't have the polarization. But when you pass through Procastars, you have new degrees of freedom, you can define polarization, and in fact, you can define a polarization in the vector potential. This polarization also is related to the stability properties. Who knows? But so far, we repeat some simulations of spherical Procastars with only one field, one complex field. And we already know that they will gonna migrate to Broglie configurations. But now what we are including is the polarization. As you can see, it's radial polarization, then split in two, start to oscillate in the main diagonals of the cubic grid, as you can see here. At the end, it collapses to a Broglie configuration when you can see the polarization in a linear configuration. It's a linear polarization. Another good thing about this simulation is that we avoid the kick, because in the migration there was a spoiler kick. Well, with simulation we avoid that. So we can even study the content of the star, because now it's not escaping of the grid. So, well, I think I'm done with that. This is all the result I want to show to you, and I hope you found it interesting. Thank you very much.
Thanks a lot, Claudio. So we have time for questions.
Okay, thank you, Claudio. Very interesting, especially about the spark synchronizations and other guise of this universal thing called synchronization that occurs in many systems. So the way that you presented it to us, which is very natural, you started with a fermionic star and then it created a scalar field, or in the second case, you have already reached star. I was thinking more about what people think about cosmological structure formation, in which typically dark matter is the seed and then baryonic matter is secreted. So if we would take that route, which is typically what people do on structure formation, although perhaps larger scale, and one could argue that this is also possible, but imagine that scenario. So let's imagine that you start with a seed that is a bosonic star, and that will have, I guess, to form in the fundamental state in that case. And then you will create baryonic matter. So do you think there would be a possibility that it would develop an excited mode? Have you looked into that?
Yeah, I'm really sure that could happen. Yeah, the thing is that while you have a neutron star or you have fermionic matter with long-lived radial oscillation, those radial oscillation will force a multi-state configuration. Maybe not multi-state, maybe multi-frequency. But yeah, I think it's very possible that we can find a multi-frequency configuration. Yeah, basically, as you said, the synchronization is something very natural that should happen, right? So, meanwhile, the fermionic part is perturbed and has oscillations it will produce due to this synchronization relation. It's independent if it's physical or cosmological is just two constants of matter, just co-gravitation. The same scenario that you are having in cosmological case, right? In principle, it's very possible. Now, then we have to ask ourselves, is multi-state or multi-frequency? That could be a more difficult question to answer, but in principle, the result of having, well, if you want to have a multi-state, you need at least the first excited configuration being stable. You have the existence of the ground and the first excited configuration. And the results that were obtained from Fabrizio and Nico about the stability of the excited configuration are also independent of the scenario. Of course, they were computed for they were computed for masses that are ultralight, but in principle, I think they can be extrapolated to other masses of the cosmological, because in the case of the cosmological case that you are presenting, maybe you need other masses of particles, maybe not. Let's see. So there is some space to ask in that case. If you have the same masses as here, that can then form astrophysical objects in long time, in late time, okay, you maybe can answer and say yes, you will form those excited states. But if the masses are different, I'm not completely sure. More or less that's the picture. And another thing is included temperature. These things we include the temperature effects in the cosmic part. Maybe the Fermi part can be included temperature due to the description of the equation of the state. But without temperature, we cannot really show if the condensation maybe will always allow the ground state and not the stable state. It's something that we also put in.
Thank you for your presentation. It was a very interesting topic. At the beginning, you showed the local convergence, and we can see in your plots that in the region there is an increase of the Hamiltonian constraint. How we can explain that behavior? Yeah.
Well, are basically I suppose that in your simulations you don't see them, right?
No.
The reason is maybe due to the method that we are using. We are using empiric methods. We are not regularizing the origin. We are not including new variables that help to regularize the equations and the origin. We are using another method from Hecuta. You know, the implicit and implicit methods, partially implicit. Have some that are non-implicit and some that are implicit. That helps to avoid that regularization and still have a regular evolution. So that maybe is the reason. In that case, as you are not regularizing the origin, the value of the fitting origin, but the errors can accumulate more there.
And another question, do you think that if you add a perturbation to your evolutions, the frequency synchronization will remain?
Yes. We did it. Yeah. I'm not presenting those results here, but we prove with perturbation. Okay. The interesting thing is that the same numerical infrastructure that we have for the accretion can be used also for the perturbation. Just increase the value of the amplitude of the field, and instead of having a big field accreting, you have a small field perturbing the system. And all of these are constraints that define at equal to 0. So we tried some tests and we found that this still works.
I have two questions. So first, I imagine that if dark matter was an ultralight scalar field, the value of the mass should be the same for every neutron star, so it should be the same everywhere. So is it possible? The mass of the particle.
Okay.
Right. So my question is would it be possible to constrain what is the mass of this particle by looking at a different example of neutron star?
Yes. That's the idea of having this.
And have you tried to do do that with existing heterosigmoid?
Not yet, but the thing is that there is a process. In this case, we have only radial oscillations, okay? But I saw in the reference there is a way to having the effects of the radial oscillations in observations. I found that there are cases where you have X-rays and some electromagnetic radiation that is affected by the radial oscillations. And maybe observing that radiation, we can extract the frequency of the radial oscillation. And if we found, for example, and that if not, it is not the one that we expected in our previous star models, and it matched, for example, with this frequency, with this value of the mu, we can start to think, okay, maybe it's coming from another component. In this case, it was only mass. You can see here, for example, in principle, the dominant one should be the worst state. It's the dominant. Will dominate the oscillation, right? Here, in the case of without scalar field, this is dominant. But in the case that you add masses, the dominant appears, but also depends on the masses. So that will give us a link. We need to find a dominant frequency not expected from our pure Nernst models, and according to this mechanism, it fits with some values, we can connect it to a specific mass of the bosonic particle.
Sorry, but yeah, maybe just on that to ask another question. But this frequency for the Sol neutron star, does it depend on the equation of states? Or?
No, it depends.
So,
but the mechanism doesn't depend. Will appear the new dominant. Right?
But what I mean is, if the equation of state can also change that kind of fundamental frequency, how do you disentangle it from, well, we're using the wrong equation of state, or we have a...
Exactly, that's why we want to find, we were looking for divergent relations.
Okay.
In the case of, okay, the thing is this, radial oscillations depends a lot in the inner structure of the star. And that means that will depend in the equation of the state. We need to find oscillations that are global, that do not depend in the inner structure, only in the global quantities, mass, radius, target deformability, those things. And for that, we need to go beyond to radial oscillations. I saw some reference that compute the difference between the fundamental and the overtone in the radial oscillations. And that difference can be universal. But that is applied in Helios model, not in this context. So we don't want to go and reproduce them because we don't know if they will appear. We prefer to go to the universal relations theory that was already developed in neutron stars and see if we can extend that using these things. So that means go beyond radial oscillations.
So I imagine that this structure made of scalar fields doesn't appear only when the star is a neutron star. So it forms, it should be even from the corner, and it should be probably oscillating in a similar way because the scalar field doesn't have an evolution based on nuclear fusion as the star. So do you expect to see well something related to these oscillations also from master seismology of let's say red giants or other kinds of stars previous to the formation of the neutron star?
Yeah, but for that depends. You have two different components, right? If you just have boson field forming the star, how is it able to represent the difference, right? In the case of well, actually Nico has a word about that. You have a canonical scalar field and also have a gaussian scalar field. Both scalar field. In the case the gaussian scalar field has a negative kinetic energy, I think. Has something canonical different, and at the end, what you have is two different kinds of scalar. And he found also the synchronization in that case. He also verified the synchronization relations, and all of them are satisfied. Even if you have only two scalar fields with different characteristics. So we think that this relation is very universal. It depends just if you have, as I mentioned maybe before, after lunch, You need a field that is modeled like a fundamental field. Yes, a scalar program could be Dirac even. If you have a frequency, a complex phase, and you make sure that you have multi-frequency or multi-state, you can find this particular differentiation mechanism, independent of the kind of demand.
But this is interesting, no? Because it would be a very different stars and they should match the same mass of the scalar field. No? So it would be. So the same mass of the scalar field should explain deviation from the expected modes in stars of all kinds, no? Not only neutron stars, but also white dwarfs or even the sun, maybe.
Yeah, it's true. But in the case of white dwarf, for example, well, let's take into account that these are relativistic effects and in a astrophysical context of some solar masses, right? And radius related to that quantity. The white dwarf, I think it is possible also to find, but you have to change maybe the mass of to have it a scalar field maybe just inside the white dwarf. Because most of our results show that the scalar field goes to the nucleus of the neutron star. You have to change a bit the parameters of the scalar field in this case. I suppose the bosonic mass particle, right?
Yeah, there's an scale argument. Like it's not the same having a solar mass neutron star in 10 kilometers and having a solar mass like the sun in thousands of kilometers compared to the mass of the boson star and how it oscillates.
I see. So it's possible that it gets diluted or.
Yeah, and actually in this scenario of fermion boson star, we do not expect that the scalar field dark matter is already inside the sequence, main sequence stars. It's more like you would agree, like you have some binary of all the neutron stars that will agree with the base pattern. So that's why if you go to the introduction, the constraints.
Constraints?
Yeah, the constraints on the mass and the range.
Okay. Here.
So there, if you look at the constraints from the gravitational wave sector, which is this green GW 1708, and you see that the radius compared to C mass is more to the left, it's more steeper. So, I mean, we would expect that if it's an old system, neutron stars, the amount of dark matter that has accreted is large. And for younger stars, I think. So the effects will be more important.
Binary relation to you.
Yes.
Let me just ask if there are some questions online. Doesn't seem like it. We still have a little bit of time. Yeah.
How big is the drift when you show the simulations at the end? They drifted. How big was it?
The drift.
Yeah, the drift for the 3D simulations.
Okay. Let me put it here. Sorry, I didn't check it properly, but this is the finest final level, and if I'm not wrong, has a semi-arrays of 15. So it's not going further, well, it's inside, so the drift in this direction is just like 1 or 2 units. And then, well, I stopped the simulation here, but watching the evolution, it seems like it's getting outside.
We had a situation where we just had that black hole. It was about 800 radius. The rise about 0.5. And we also saw this drift, which was about 10 times true. But then it seemed to stagnate, so it did something else. But the black hole moved, that's for sure. It didn't seem to be physically relevant to something else by variance because it was just a black hole. But we also saw this drift. Although it was much lighter. Yeah. But also the black hole is more compact.
Could be
And our level of measure 5 was much smaller because of
I suppose that it also move along the diagonal of the.
I don't know. I don't know. I just.
Okay.
The distance, for example, we can also do this.
Okay.
Right, so since Claudio will be here for a few weeks, I suggest we stop here and thank him again. And we'll see each other tomorrow morning for the next seminar.